Keene State College Faculty Student Scholarship Seminar of the academic year 2021-22 for students registered in the IS 199 course that are here tonight. Please sign up on this attendance sheet before you leave. I'll leave it right here in the front. That way I'll make sure that I know that you were here in person tonight. Also, a number of students came up to me a few weeks ago when I think it was last year, and they asked me whether the assignment sheet, the 4-page, 5-page assignment sheet can be put up and made available to them. I've made that available. It's on the Canvas site. If you want to write your paper soon, it's right there for you. If you have any questions about it, please ask me. If you're here via Zoom, I want to remind you, please, to mute your microphone and to turn off your camera, at least for now. At the end, if you'd like to ask questions of the presenter, please just put something into the chat, or you can raise your hand icon. We'll unmute you, and then you can talk straight to the presenter. Tonight's speaker is Dr. Fernando Dalama Gonzalo. He's an assistant professor in the architecture program here at Keene State. Dr. Dalama Gonzalo earned a master's degree in renewable energy at CEU San Pablo University in Madrid, Spain. And he earned his PhD in architecture with an emphasis in acoustics, which is what we were just talking about, at the Polytechnic University of Madrid, Spain. Dr. Dalama Gonzalo came to Keene State in 2018 after serving as chair of the architecture department at the American University in United Arab Emirates. The courses he teaches here at Keene State include architectural design, architectural representation, architectural systems, and solar design and building science. He's a very prolific author with 15 journal articles, either sole or jointly authored, and he's got 5 patents to his name, which is something I didn't know. His research centers around energy simulation, monitoring systems, active noise control, and the simulation of acoustic behavior in concert halls, among other things. Tonight, he'll talk about materials and their contribution to energy conserving buildings. And tonight's talk is titled Life Cycle Assessment of New Materials to Achieve Zero Energy Buildings. Please welcome Dr.
You, Mike. Well, it's a pleasure to be here and to speak about my research. So something that Mike has mentioned, we're going to talk about this today because I'm going to talk about some of the articles that I have published in Keene State College, working with other institutions and working with Keene State students. And all this stuff that I'm going to show today, it's about patents as well. So having 5 patents sounds great. You might think that I'm a wealthy person, but I'm not. Okay, so probably because I failed, I did something wrong. But having patents doesn't mean that you become rich immediately. It's a long process, and I will talk about patents today as well. Okay, so let's start. I'm going to talk about these new materials in architecture, and I'm going to talk about life cycle assessment, and I'm going to talk about zero energy buildings. So this is a concept that it's new. Well, it's not new, but it's mainstream nowadays. All countries are working towards the zero energy building. It's a very simple concept, but it's very difficult to achieve. Okay, so how can we do it? There is not a recipe. I cannot do, you have to do this and then that, and you have to go this way, and then at the end you have a zero energy building. It's much more complicated than that. And I'm going to show you what a zero energy building is and how new products can help architects or engineers to achieve this concept of a zero energy building. So let's start by, well, this is what I want to show you. This is all the work that I'm going to show here is not something that I did in 1 year or a semester. It's like a 15-year work. Okay, so when I was in Spain teaching architecture, I had I was lucky because I was a member of a multidisciplinary research team with engineers, architects, and we started developing a new product. We call it water flow glazing. I will talk about this product today. And it was new. It was a new product in the construction market on the verge of recession. Okay, so that's the worst idea you can have. If you want to include or if you want to implement a new product in the construction market, when you have a recession inside, please don't do it. But we did it. We were young and unaware, and we did it. We patented the system first in Spain, then in Europe, then in the United States, and we started working on that system. And what I'm going to show now is the process. It's a 15-year process. And well, first we have a hypothesis. Okay, so we have a new product. How does this product work? We thought that we can build a glass box in the middle of the desert, and we can have comfort inside this glass box without consuming any energy. That was the hypothesis. The engineers, the software engineers, developed a mathematical model because, well, in the world, in the software world, that was feasible. But is it real? Can we do that? And then we built prototypes. Okay, so we have been building prototypes for 10 years. And now we are getting results from those prototypes. And what we are doing here with the Guinea State students, we are analyzing results from these prototypes. And then we are trying to validate both the first hypothesis and then the mathematical model. Okay, so this is what we are doing. In Guinea State College, we are analyzing results. Okay, we are not building the prototypes. I will show you a couple of them. We are analyzing all the data. We have sensors everywhere, and then we are analyzing all this. And I'm going to show you the results and how we can apply those results to design zero energy buildings. And we have published, I'm going to talk about these 4 papers that, well, actually, the students that collaborated with me were Danielle Pinet and Matthew Griffin. Danielle, I think she graduated in 2020, and Matthew is a senior student. We are thankful because we have had, well, I have had faculty development grants, and they have gotten some student stipend grants. So thanks to these grants from Guinea State College, we were able to work on that and then to publish this in open access journals, which is quite expensive. But we did it in 2 journals, Energies and Sustainability. They are Q1 and Q2 in Scopus, so they are pretty good journals. And I'm going to speak about these 4 papers that we have been publishing between 2020 and 2021. Well, first, I have to explain what the water flow glazing is. Again, it's a crazy idea. We try to, well, the traditional double glazing, we have 2 panes of glass, and then we have an air chamber, or we can fill this space between 2 glass panels with other gas, argon, but usually we have air, okay? So we have the glass and we have the thermal insulation that is tiny. We are talking about a ½ inch or something like that of air or gas can provide us with. Instead of having this air or gas cavity, we fill this with water, and it's not just a field with water. We move this water. Why we do that? Well, if we think about this system from the summer perspective, we have to consider that we want to protect the building from the summer sun, from the summer hot temperatures. So if we manage to keep the water temperature of this cavity below the comfort temperature, there are a lot of things that are happening here. First, water is transparent to visible solar radiation, but it absorbs heat. Okay, so basically, if we have water inside this cavity, The solar radiation, we can, the light, the solar radiation, the visible part of the solar radiation enters the building because water is completely transparent, it's visible, but water absorbs the heat of this solar radiation, the infrared solar radiation. So that's amazing because we can have transparency without the heat that comes from the sun. So if we think about office buildings, skyscrapers made of glass in southern countries, this can be the perfect solution because those buildings are completely ineffective when it comes to analyzing the heat, the cooling loads in summer in hot countries. Having glass high-rise buildings is the worst thing you can do in terms of sustainability, but people do it. Okay, so if people keep on doing wrong things, let's try to invent or create something that can prevent this bad decision from being even worse. Okay, so that's what we did. And from the theory, it works. We can have a transparent box with glass, with water between these two glass panes, and water will absorb all the heat, and all the light, all the visible light will go through the glass. So this is the concept of the water flow glazing. So this is the first paper. So first, I'm going to show you how we try to validate the mathematical model. This is a new product. The theory, it works. You see the spectral properties of water, the spectral properties of glass. You say, okay, this might work, but we have to make sure, we have to validate. So what we have done is to create these two different prototypes, and then we are validating the mathematical model to validate the hypothesis that we can create a glass box in the middle of the desert without consuming any energy, and you will be comfortable inside. So this is the first prototype. We call it Peralveche. Peralveche is a nice, well, it's not nice, but it's a very small village close to Madrid. We were friends with the mayor, and we ended up building something here. And this is what we did. Okay, so the first prototype was a cabin. When we are talking about prototypes, we think of 3x3 or 1x1, sorry, foot box. And this is a cabin. Okay, so actually you can enter this cabin. It's like 7 feet by 7 feet. Okay, so you can be there. You can't leave. It's not a house, but at least it's a cabin, and you can enter and you can feel the temperature, and if it's too warm or it's too cold. So you can stay there for a while and feel the temperature and the weather conditions, if the weather conditions are changing. We have two prototypes or two cabins in the same place because we wanted to compare the water flow glazing and a traditional double glazing. So that's why we built two different prototypes. One of them is connected, so the water flow glazing cabin is connected to geothermal heat exchangers or borehole heat exchangers. Another crazy idea. Why? Because the temperature below, let's say 20, 30 feet is constant throughout the year. So if we have water running through the glass and we can transfer the excess of heat that we have in this glass box to the ground, that's perfect because the temperature here, and its comfort temperature is around 60 to 70 Fahrenheit. Okay, so 30 feet, 40 feet below the ground level, we have a comfort temperature. So what if we can transfer the excess of heat that we have in our glass to the ground? Yeah, so we thought it was a good idea, and we did it. We built two cabins, one with the same, exactly the same glass, the same cavity, one filled with air, the other with water, but we have to move this water, okay? Because the sun heats up the water, and then we have to transfer that heat to the borehole heat exchanger. And this is it. First thing, don't do that in your backyard, or if you do it, it works, but you have to consider the soil. and we didn't know that. We thought that it was going to be easy, but we found the worst soil on earth. It was rock, but at the same time, it wasn't stable. Okay, so we dig this hole, 100 foot, no, 100, it was, yeah, a 200 foot high hole, very narrow, something like this, all the way down. And first we need to break the rock, but at the same time, those rock is not stable. And when we took out the device that was drilling, the hole crumbled. So we had to do it again and again until we found, we figured out how to stabilize the walls of this. Okay, it took a lot of time, a lot of money. So first you have to analyze what kind of soil you are working with, because sometimes it's not worth it. Okay, so the money, the time you spend on drilling holes, it's not worth it. And we did it. Then we introduced these pipes. So we had the perfect heat exchanger between the hourglass and the soil. This is the cabin, by the way, because the first question, I take it for granted because I've been working with this for 15 years. But the first question is water transparent? Do you see waves, or do you see the water moves, or you can't tell whether you have water or not inside this glass? Okay, so in this picture, we have 3 walls, the south elevation, the east, the west, and even the roof. They are made of glass, and you can't tell that the glass is there and the glass and that the water is there and the water is moving. Okay, you can't tell. And we built these 2 cabins, the one with water flow glazing, the other one with traditional double glazing, and okay, and we run it. What is the mathematical model? Well, I don't want to explain this that much, but basically, when we are working with glass, there are 2 parameters that we have to keep in mind. The first parameter is the thermal conductivity, this U value, and the second one is the G factor, or I think G factor is a European concept. Here is the solar heat gain coefficient. It's the same. It's the amount of solar radiation that enters a building, the solar heat gain coefficient. Okay, in traditional glass or traditional walls, these 2 values, well, these only, we only have a solar heat gain coefficient when we have transparent. When we have a brick wall, it's not transparent, so the sun doesn't go into the building. But in transparent, in windows, curtain walls, those 2 parameters are fixed. They don't change. The thermal transmittance depends on the thermal conductivity and the thickness or the width of the glass panel. And the solar heat gain coefficient depends on the optical properties of the glass, and they don't change. But with water, we can change it. Okay, so that's why we call this a dynamic U and G, or solar heat gain coefficient, because it changes. It changes depending on the mass flow rate. Okay, so we can control the amount of water and the velocity of the water running through this. And with this, we can change these 2 properties that are fixed. Okay, so this is the first thing we have to understand. We're doing something that have never been done before, changing the thermal conductivity and solar heat gain coefficient of glasses by circulating water. And we needed a mathematical model. So well, they came up with formulas, and everything is, so this M, it's the mass flow rate. Okay, so in all these formulas, we have the mass flow rate. So by changing the mass flow rate, we can change the thermal conductivity and the solar heat gain coefficient. And this is what happens. Okay, so we have, this is the G factor, the solar heat gain coefficient. This is the thermal transmittance. So if we stop the water flow, we have a value. And this is what when we look at the catalog, we see this value, because there are no catalogs of water flow glazing yet. So we have a fixed number. So in this case, it's 1. The units are international units, and the other one it's 5. Okay, so 1 it's a pretty good one. 5 it's a very but when it comes to thermal insulation, 5 is too high. Why? 1, it's quite good. But changing the flow rate, we can bring down the thermal conductivity up to almost 0 in this case, and up to a very good value in that case. Okay, so we can improve the thermal conductivity by changing the flow. There's an optimum flow. So here, if we keep on increasing the water flow, the velocity increases. That can damage the circuit of water. So there's a moment in which we set the optimum flow rate, water flow rate. And that happens with the U value, the thermal conductivity, and the G factor, the solar heat gain coefficient. So we have an optimum. And the solar heat gain coefficient, we have different classes. We can go from 0.2 to 0.6. Okay, 0.6, it's something transparent, is the glass that we have in our windows. 0.2, it's like something similar to sunglasses. Okay, so it's a very low solar heat gain coefficient, and it's not transparent. It's almost opaque. You can see through it, but it's too dark. But everything that is above 0.6, it's quite transparent. Again, we can bring down the G factor, but taking into account the thermal, not the visible. Okay, so we can have the same effect that we would have with the sunglass with a transparent glass. Okay, so the sun is not bothering, but it's completely transparent. So that's why we want to do this. We can bring down the thermal conductivity, the thermal transmittance, sorry. We increase the thermal insulation of glasses, and then we can bring down the solar heat gain coefficient, which is very convenient in summer in hot countries. Okay, but if in winter we need to increase the solar heat gain coefficient again, we can do it by stopping the flow. So that's why this is dynamic. We can change these two properties that are static. They don't change, but we can change it by changing the weather. And this is it. So we have two wonderful graphics. What does it mean? Well, when we look at this graphic, we say, okay, my God, we can't believe this. Why? Because, well, this is the inlet and the outlet temperature. Okay, so we have this is the inlet temperature. So this is the temperature when the water enters our glass. And this is the temperature when the water exits the outlet temperature, okay, when the water exits the glass pane. Well, those are international units, but it's quite good because the temperature is between, the inlet temperature is close to 18 and the outlet temperature is close to 23 Celsius. We are talking about Celsius. This is from 68 to 72 Fahrenheit, which is perfect comfort. Okay, so our running the water through the borehole heat exchangers, we have water at a comfort temperature, which is amazing because we don't spend any energy on it. We don't have an HVAC system. We don't have heat pumps. We don't have anything. Just run the water. We have a water pump, but the electricity that these water pumps consumes is ridiculous. Okay, so by having or by consuming zero energy, practically, we can have comfort. We can have a comfort temperature in a glass pane. But if we want to translate to this graphic to the indoor temperature, things are not doing so well. And this graphic, we have the gray line is the outdoor temperature. The outdoor temperature, it's Spain, wonderful weather. It's around 35 Celsius. 35 Celsius is 95 Fahrenheit. Okay. The red line is the temperature of the reference cabin. So the cabin without water flow glazing. So the temperature is 55 Celsius. 55 Celsius, it's around 140 Fahrenheit. Okay, so you can't live there. So that's true. If you have a glass box in the middle of nowhere, in the middle of the desert in Spain, and you have a lot of sunlight, you can't live there because it's too hot. You need an air conditioning system. It's impossible. Okay, We thought that the indoor temperature in our cabin, in the water flow glazing cabin, was something between 24, but no, it was actually higher than the outdoor temperature. So the blue line is the temperature inside the water flow glazing that reached 37, around 98 Fahrenheit. So it was too hot. Okay? So can we have comfort without consuming energy in a glass box in the middle of a desert in Spain? No. With this glass, okay? But that was in 2010. So we were still young, and we kept on working on that, okay? At the same time, we have this formula there. So this is the outlet temperature. So we have a lot of parameters. And it was a success because with the mathematical model, we could predict the outlet temperature knowing the inlet temperature. Okay, so this was not successful because we thought that we were going to have comfort. We don't have comfort, but at least we can validate this formula and we can predict what happens inside the water flow glazing. Okay, so yeah, we kept on working, and this is the okay. Now this was in 2010, and this prototype was built in 2017. Okay, so 7 years later, we are now involved in a European project, the Horizon 2020, and it was a 7 million euro project. It's not for me, so I don't have 7 million euro. It was for different institutions, the Polytechnic University of Madrid, the Fraunhofer Institute from Germany, some facade engineers in Bulgaria. So it was, well, it's not multidisciplinary, but multi-national project. Okay, so there were like 5 or 6 different institutions from 5 or 6 different countries. Anyway, now that was the goal. We are building a prototype. It's not a prototype, it's an actual building. Okay, so it's a 30 by 30 feet glass box for sure. And the technology is the water flow glazing. But now with the double glazing, we can't have comfort. So we ended up thinking that having a triple glazing would be a good option. Okay, so we changed the technology. And we added an air chamber. Well, it's filled with argon. Okay, so we have the properties of the water, and we also have the properties of the gas cavity between 2 glass panes. So we are using a triple glazing. Well, here at the TDS Center, we have triple glazing. So in cold countries or in countries that are demanding from the we have a demanding weather. It's either too cold, too hot. We can use triple glazing. It's not something weird, okay? But with the triple glazing, we did this. And it's not just, the project was not just about analyzing the properties. It's about creating a product. And now this product is in the market. It's completely reliable. We don't have any leaks. We have all the warranties in the world. Because people from Germany, from Bulgaria, from Spain, from Finland, from Denmark, I don't know, 5 or 6 different countries, we're working on this. Okay, so now it's an industrialized product and it works. Nobody's using it yet, but it's in the market. And we have this, the project. Okay, the project includes this circulating device. And yeah, because but everything is included in the same frame, so that simplifies a lot the piping systems. Okay, because everything is within the frame, and we only have to connect, like we connect a radiator or something like that. Okay, so yeah, the best definition of this product is like it's a giant, transparent radiator. You have your hot water, your cold water, whatever, and you just plug your panel into this piping system. And but this is not just the borehole heat exchangers and that's it. No, here we have a lot of things. We have heat pumps, we have heat exchangers, we have solar PV, solar panels. And we have buffer tanks, water tanks there. Okay, so everything is connected, but all the facade is the three elevations are made of this water flow glazing and the internal partitions. That's another thing that we are trying here. Not only the envelope, but also internal partitions. The walls, we have an office space, so we have different divisions, and the divisions were made of water flow glazing as well. Okay. And everything is connected. It's connected to the tank, it's connected to the heat pump, heat exchangers. Then with the PV panels, we produce the electricity that we need to cool down the water in the heat pump. Okay, so this is a zero energy building, and it is a zero energy building. So at the end of this presentation, you will realize that it is a zero energy building, but at what price? It's complicated. And this is it. So we have this panel. The size, it's like a 11-foot high panel. And then we use a crane and we plug it in the system. So the technology, this technology is meant to create skyscrapers, not just a one-floor building in the middle of the forest. Okay. But yeah, the technology is there. And this is the opening ceremony. People are happy, but they are not. They are smiling, but well, it was having this on time with all the pressure from the European Union. It was something crazy, but what did we do first? Again, validate. We have the same formula. Yeah, in Photovoltaic in Spain is working, but will it work in Sofia in Bulgaria? Let's see. And here we have the inlet temperature, the outlet temperature, and here we have the difference between the actual temperature and the simulated temperature with this mathematical model. So it works. Okay, so from the simulation point of view, we are happy because our system, our monitoring, our simulation system, our simulation tool works. And we can predict not only the outlet temperature, but how much energy we are absorbing. Okay, we can, that's another good point of this water flow glazing technology. We can heat up water. Okay, so we are producing renewable energy by heating up water. It's like a traditional solar thermal panel, but transparent and on the facade. So we can understand in winter and summer. So this is in winter. The green one is in winter. The black one, it's in summer. We compare the actual results and the simulation results. So it's almost the same. So we can understand how much energy we are going to get from our panels. And this is renewable energy and that we can use for domestic hot water or for the heating system. We can use this energy. It's water, it's hot water, but it's renewable energy. So this was the second paper. The third paper, we have to evaluate two things: the thermal comfort in this pavilion. It's not a prototype. And there are people working in this 30 by 30 glass cube in the middle of Sofia. Okay? So we want to evaluate the thermal comfort and the life cycle assessment. The life cycle assessment is, yeah, we have this, it's a zero energy building, but we have to analyze first the investment, the money that we have spent, the money that we are saving in the long term by saving energy. And then we have to analyze the energy that we save and the CO2 emissions that we save. Okay, so this is the life cycle assessment. And to understand if the technology is good or not, we need to analyze the behavior of this technology over a period of 50 years. And well, first, the comfort. We are in a glass box with a glass facade, with glass partitions. Everything is glass. Okay. Is it comfort? Do we have comfort there? Well, the ASHRAE, the American Association for Heating and Cooling, or I don't know, well, ASHRAE, came up with this concept, the mean radiant temperature. Okay, so we have the air temperature. We can have a thermostat somewhere, and we have an air temperature. I don't know the air temperature of this room, but I'm sure that it's a comfort. Okay, But the mean radiant temperature is the temperature of the walls, the ceiling, the floor. It's like an average, and it depends on the position of people. Okay, how this wall is affecting me. If the temperature of this wall were different than the temperature, than the air temperature, and I'm close to this wall, I'm affected by this temperature. But if I'm far from this wall, I'm not affected. Okay, so dealing with this mean radiant temperature concept is complicated because we need a lot of sensors. We need sensors everywhere because we need to understand how the temperature changes from this corner to that corner, and from the ceiling and the floor, and this point and that point. So we have a lot of sensors. And then we have to analyze how the feeling or how people feel that temperature depending on the position. Okay, so we have different temperatures. We have walls at different temperatures. So depending on the position, you can feel something or something different. Okay? It's quite difficult to understand and to work with the temperature and the angle factor. Okay, so we have to divide the floor, the ceiling, the walls in different parts, and then we have to, every number, it's a different sensor, it's a different temperature. Okay, and then we have to analyze the angle factor between this rectangle and this guy, and this rectangle and that guy. Okay. Well, we did this, and well, those are all the sensors. So we have the roof temperature, or the ceiling temperature, the floor temperature, the wall temperature. These are the glass, because we are cooling down the temperature of the glasses. Okay, we are talking always about summer. We are cooling down the temperature. So at the end, with all these temperatures, the blue line is the mean radiant temperature. Those are actual data, and these are working days. Okay, so the building starts operating at 7 a.m. It ends at 8 p.m. During the night, we don't have anything connected. The system is off. And this is the mean radiant temperature, which is around 20 Celsius is around 70 Fahrenheit. Okay, so it's pretty good. But we're not done yet, because to evaluate comfort, we have to use the predicted mean vote. Again, it comes from ASHRAE, kind of. Well, we found out that these guys in Berkeley, they have developed a tool to analyze the predicted mean vote. Okay, so we used it. At least our software engineers, they were exhausted, and okay, let's use the Berkeley tool. And well, they came up with this concept, the operative temperature, that depends on the air temperature and the mean radiant temperature. We have the mean radiant temperature, so we can calculate this operative temperature, and we can put it here. So it depends on the operative temperature, the airspeed inside the building, the relative humidity, the metabolic rate, the golfing level. So there are a lot of factors, and you put all this into this tool, and you get the predicted mean vote there. The predicted mean vote, it's a survey among thousands of users. It's about the comfort feeling. Okay, so if you are at this temperature, with this relative humidity, with this radiant temperature at this point, how would you define your comfort sensation? Excellent, very good, good, whatever. So after thousands of surveys, they came up with this, and now there's a model that can predict, if you have all these conditions, you can predict how people are going to feel within your room. And well, basically, the green line is the predicted mean vote. 0, it's optimum. Okay, so if your predicted mean vote is 0, it means that 100% of people in different countries in the world would say that this is a perfect comfort condition. The values that we are targeting are -5, minus -5, sorry, and positive -0.5, and positive 0.5. Okay, so if we are within -0.5 and positive 0.5, 98% of people would be in comfort. So this is acceptable. Okay, so we run the simulation and we are within this rectangle. Okay, so when the system is operating, you can see that when the system is not operating there at the beginning, it's too hot. Everything that is above 0.5 is hot. Everything that is below negative 0.5, it's cold. We are in summer. Okay, so if you don't do anything, the predicted mean vote is that it's going to be too hot. But by doing this, we found out something very interesting. The gray line that we have there, okay, so this gray line, this one, and this one, this is the air temperature. So this is the temperature that our thermostat is giving us. Okay, so it's the temperature of the air. It's around 28, 20, 27, 28 Celsius. This is 84, 85 Fahrenheit. Okay, so if you set your thermostat at 85 in summer in your office, you will be, it's too hot, I can't work here. But with a mean radiant temperature, if you are surrounded by glass at that temperature, at 20 Celsius, at 70 Fahrenheit, your predicted mean vote is slightly cold. It's below zero. It's from 0 to negative 0.5. Okay, so even with a temperature that is crazy, 85, nobody sets the thermostat at 85 in summer. It's too hot. Well, if you set your thermostat at 85 and the surrounding walls are at 70, you feel that it's slightly cold. That's good because the lower the air temperature, the more energy we need to spend to get to that temperature. In winter, is the other way around. If we set our temperature at 75, we are spending more energy than if we set the indoor temperature at 72. Okay, so in summer, instead of setting the temperature at 74, 75, we can set the temperature at 84, 85. And if you are surrounded by this water flow glazing, you feel good. So this is the comfort. If we evaluate the life cycle cost or the life cycle analysis, the life cycle analysis includes three different analyses. We have the cost, we have the energy, and we have the CO2 emissions for the equivalent CO2 emissions. The time frame, 50 years. Okay, so the three formulas are the same. We have the initial value. So this is the money that we have to pay up front for the energy that we are consuming when we are building the office space or whatever. And these are the emissions during construction. And then we have the operating period. This is the money that we are spending on energy, heating and cooling. This is the energy that we are spending over 50 years. And this is the CO2 emissions that we are emitting over 50 years. And finally, we have the money that costs the demolition of the building, the energy that I need to demolish the building, and the CO2 emissions that we have when we demolish the building. Okay, so imagine that we build something here, and in 50 years, we demolish the building and we take it to all the waste thing to landfill. So this is the life cycle analysis. We have to analyze cost, energy, and CO2 emissions. And we have done this with the first prototype, the Transmittance one, and with the Sophia prototype. Well, if we look at this and this is the water flow glazing, and this is the reference project. So this is the same project with the traditional double glazing. Well, we can understand this is the energy. Okay, this is the energy. This is the emissions, and this graphic is about the cost. So we can see that we save a lot of energy. So this is the energy that we will consume with a glass box in the middle of the desert. With a double glazing, And yes, so the energy that we consume in a glass box with water flow glazing in the middle of the desert is much less. Okay, that's fine. And well, the CO2 emissions and the energy, they are connected. Okay, so if we reduce the energy, we reduce the CO2 emissions. What about the cost? Okay, eventually, after 50 years, yeah, you can say that this decision pays off. But believe me, no client, no construction developer would agree with that. You say, no, in 50 years, you will start earning some money in 50 years. Crazy. Okay. And this is with the first prototype. With the second prototype, we don't get to earn money after 50 years, okay? Because the system is quite expensive compared to a double glazing. We have good savings in energy. We have good savings in CO2 emissions, but the cost is we can't compete. So this product nowadays cannot compete with traditional glazing unless the energy price continues to grow. It can happen, maybe. But, well, this is it. It works from the comfort point of view. We save energy, we save CO2 emissions. The cost is not, it's not competitive so far. So we have to reduce the cost of manufacturing these panels, or the price of energy has to increase. Okay. Well, if both things happen, probably it will become a competitive product. If not, no. Finally, what is the paper for? We get the Sofia Pavilion again, and we are analyzing in terms of zero energy building. What is a zero energy building? It's very easy to understand. A building that consumes less energy that it generates, or a building that generates more energy than it consumes. Okay? We are talking about renewable energy. So if we have a lot of solar panels, if we generate energy, if the energy that we are generating is more than the energy that we are consuming, it doesn't have to be at every single moment. It's over a year, okay? Because in summer, if we have solar panels, we generate a lot of electricity. In winter, maybe we don't generate electricity. But if we have the balance from January to December, if we generate more energy than we consume, this is a zero energy building. So is the Sofia Pavilion a zero energy building? Well, let's analyze. These are the heating loads. Okay, so we have, this is the year from January to December. If we have something, this is zero. So everything that is above zero, it's heating. So we need this heating demand. Everything that is below zero, it's cooling. Well, it's interesting. Even in January, with a glass box in the middle of Sofia, it's quite cold in winter. But even in Sofia, in winter, in January, in a glass box, there are moments in which you need cooling. In sunny days, if you have a glass box, you need cooling. If it's an office space, there are a lot of people working with equipment, with computers and all that stuff. You might need heating. And this is what happens in office buildings in Boston or in New York. We have these skyscrapers. They have the air conditioning on in January, when outside we have negative 25. Okay, this is insane. That happens. Of course, in summer, we need a lot of, well, this is a comparison between the reference cabin, okay, or reference pavilion with double glazing, with traditional glazing, and this is with triple glazing. So we reduce the amount of energy that we need. And what is the orange bar? It's the hot water that we can produce. Okay, so the hot water that we produce is much more than the electricity that we need to operate the building. I know people say, yes, but this is hot water. Why would I need tons of hot water in summer? Yes, in summer we get rid of hot water, or we can sell this hot water to the neighbors, or we can heat up an Olympic swimming pool. But yeah, in winter it works, because in winter we generate more energy in terms of hot water than the energy that we need to heat up the building. So it's good. But can we count this as renewable energy? Well, if I want to sell my product, I can count the hot water that I produce in July as renewable energy. Yes. Okay. But I'm honest today. I decided to be honest. So I'm going to do something different. And I'm going to look at the PV panel production. Okay, so the PV panel production, these are graphics in January. We have January here and July there. Well, deciding the orientation of the PV panels matters. And we didn't want batteries. We could have added batteries, but then the life cycle cost would be even worse than it really is. So we don't have any batteries. And yeah, we do this. This is the demand. The yellow bars are the demand, the daily demand in winter and in summer. And the blue ones is the daily energy production. So the best thing would be something like that. If we can match the demand and the production, that would be great. Okay. In winter, we can't do that because so in the evening, we don't have any sun. So here we have the demand and we don't have any production. This is a sunny day in winter, and this is a cloudy day in winter. So if we don't have any sun, we don't produce solar energy, we have the demand. But in sunny days in winter, using the right orientation, the balance is positive between the energy that I need and the energy that I take. Again, what I do with the excess of this electricity, I can give it away to the grid, or, well, I don't know. But the balance is positive. Okay, so if we take into account only the electricity, it's positive. If we take into account electricity and hot water, it's more than positive. But keep in mind that the cost. Okay, so I can't tell a client, yeah, save the planet. Well, I can tell him, and no problem, because in 60, 70 years, you will return your investment. Doesn't make sense. If the return of investment is more than 7, 8 years, nobody goes for renewable energy or zero energy buildings. So this is our commitment now. So we know how to do it. Yeah, technically, I can design a zero energy building. I can spend a lot of money, and our client can save a lot of energy, and perfect. But we either meet, I don't know, saints that I don't mind. The money is not my concern. I just want to create a building, the best building possible, saving energy, saving emissions, and I don't mind the electricity bill or whatever. Well, if you find someone like that, introduce it to me, because I will be willing to shake their hand. I haven't met any yet. So that's it. What are the conclusions of all this stuff? Well, we know how to design zero energy buildings, and we have the technology. Okay, we can do it. But we have to consider the architecture design. We have to take into account the location, orientation, the use of the building. And if we are working with glass, selecting the right glass, it's very important. It's easier designing zero energy buildings with opaque envelopes. It's easier because we can provide the envelope or the wall or the roof with a lot of thermal insulation. But using glass, it's a challenge, but people like glass. Okay, if you look at contemporary architecture, the use of glass is massive. And then, what about the water flow glazing technology? We require a monitoring system, because we only understand if we are saving energy if we can monitor, or we know the energy that we are producing and we are consuming. Okay, without a monitoring system, we don't know if we are designing zero energy buildings. And finally, a life cycle assessment. Yeah, we have to keep in mind that we need to understand the cost, the energy, and the CO2 emissions over 50 years. And saving energy, I think it's easier. Now the challenge is to reduce the cost, integrating renewable energies, and at the same time not increasing the cost of the project or the money that our client has to pay upfront. Future work. We will be working with students, and we will keep on analyzing data, and I will keep on publishing articles with students. And if you still continue with this program of the student stipend or faculty development grants, it will be great because they will give us the chance to publish. The goal is always to attend an international congress. We haven't done this over the last 2 years, but well, if things are looking up, probably next year we will apply for an international congress, and we can show this what we do in King State College in international congresses on energy efficiency and zero energy buildings and all that stuff. Thank you very much.
We have questions.
Yes.
Thanks, Fernando. I've got a couple of questions, and I'll try to group them together because I think they're related. I noticed the flow of the water is bottom to top. I wonder if there's a specific physical reason for that.
No, and it's a good question because actually it doesn't have to be bottom up.
Okay.
It doesn't have to. And believe me, sometimes we go the other way around. It doesn't make any difference. The only difference is about the water pressure, the hydrostatic pressure.
Right.
We have to keep that in mind. That's the only concern. So depending on the hydrostatic pressure, we have to either go up from bottom up or up bottom. It depends.
And I noticed the gap that you're filling with either air or water was 16 millimeters.
Yes.
So even for a pretty big window and a cabin, it's not a high volume of water, right?
No, it's
I don't
not.
want to have you do the math on that, but we're not, it's not an ocean.
No.
Do you have to purify? Are you filtering and cycling that somewhere underneath?
That's another good question. You know too much about this. It's not only, we call it water, it's not water. So if you drink that fluid, you die because they're antifreeze, there are purifiers, because water is the origin of life. So if you leave water there, a lot of living creatures will appear, and maybe it's nice from the architectural point of view, but it will spoil the flow of water. So it's not water 100%. So
That could lead to some interesting stained glass, couldn't it?
Yeah.
Thanks. And then last question, just while I got the mic, the cost. Is there a key driver to that, a material manufacturing? Is there something that's the linchpin to having that cost?
Well, it's something expensive, but the question is compared to what? If you compare a triple glazing with water to a traditional double glazing, it's impossible. If you compare a triple glazing with water with a triple glazing without water, yeah, it's higher. And now I think the key point is about the circulation device. It's too expensive. If we take the circulation device from the frame, it's not that much. Maybe it's 10% more than a traditional triple glazing. But the circulating device nowadays, it's but we haven't found the technology to lower that price. But I think this is the key point. The frame is the same as a triple glazing frame. The glass itself is not thicker than a triple glazing. It's not that much. It's the device, the circulation device that increases the price.
Thank you.
Thank you, Jim. Yes.
So in the triple glazing, you had a layer that was like argon. Is that also circulated? Is that something you have to replenish, or is that sort of fixed and just stays.
The argon, yeah, the argon doesn't circulate, it stays. Argon, it's not something crazy. Probably the glass that we have in the TDS Center, I'm speaking about the TDS Center because I teach there, and it's quite a nice building, and it's a LEED platinum building. So probably this, it has an argon chamber, and it doesn't circulate.
And that's not something you have to replenish after some time. It's sealed in there and cannot leak.
No.
You talked a little bit about return on investment and how, no investor would want a 50-year return.
Mhm.
What tends to be kind of considered like the industry gold standard that within how many years would?
Less than 10 years.
Yeah.
If you mention 10 years, your client panics. 10 years. 5, perfect, they go for it. 7, 8, it's something 7, 8 years. It makes sense because 10 years, it's where would we be in 10 years? We don't know. 5, it's something, yeah, but I don't, it's psychological. 11 years, forget about it. 9, okay, it might work. But less than 10 years, it has to be less than 10 years. 50, it's impossible. 50 years, it's insane. Nobody will do it.
And do you find the appetite for it being a longer return exists in places, like I know Keene State a number of years ago made a commitment that any new building would, meet LEED standards and different things. Do you find that sometimes when someone can use it as part of their marketing or part of their values, that they're willing to accept, a longer return on investment?
Well, in Europe, it's different than here. And there's something that I don't like. In Europe, there are a lot of subsidies. So probably a technology that is not effective, that it doesn't have a good return, it can become competitive because of the subsidies. So we have the same in Spain. If you're an entrepreneur in Spain, you have to wake up every morning and you have to read the official paper of the government, because here they publish all the subsidies there. So it's about, okay, you are creating clothes, for example. You are, okay, so there are subsidies for jeans. Okay, so let's start producing jeans. Or today there are subsidies for sunflowers. My family work in the agriculture field, and they say, okay, this year we have to plant sunflowers. Sunflowers in the middle of Spain. Nobody has done that ever yet, but there are subsidies. So let's do it. That's insane. So I don't believe in that system. But if you have good friends in politics, maybe I shouldn't say that, you can make this technology competitive, or any other technology. Because if the government or someone decides to subsidize this technology, it immediately becomes competitive. Is it good? I don't think this is the right, I think it's better if we continue to develop this and we bring down the prices and we make ourselves competitive. So I think it makes more sense. But in Europe, you can wake up one day, you can read this newspaper and say, wow, they are subsidizing my technology. So let's go for it.
So talking about cost gets to my question. In the course of your talk, you showed us beautiful slides of really nice looking prototypes and aesthetically pleasing. And the job of constructing them and doing the boreholes and everything, like it seemed like a lot of work, but it seemed immensely interesting looking and I'm guessing enjoyable.
Mhm.
So I guess my question is, where does the funding for exploring prototypes in this way come from? Is it government funding?
Good question. When we were young, back in 2010, we invested a lot of our money. Okay, so the first prototype is on me and my team. Wow. Okay. Why? I told you, we were young, we were, for the second one, for the one in Sofia, it came from a Horizon 2020 project from the European Union, subsidies, 7 million euros. And probably more than 500,000 were spent on that prototype. doesn't make sense. It's a prototype, it's a 30 by 30. It's extremely expensive, but it's a new product. We had to develop the frames from scratch, so we didn't have anything. So it was too expensive because we had to create. Now, if we have to do the second one, a second building like that one, maybe the cost would be 1/3 than the original cost. But the funding came first from our pockets. We lost a lot of money with this. I lost a lot of money. And second, from the European Union. They invested a lot of money before 2020 in this program for new materials, from energy efficiency. And well, of course, we are grateful because we have been working on that for 5 years with good funding for materials, for people working on this. But now my question is, what now? The project is done. We have a product. Who is in charge of following up? Is that wasted? 7 billion euros? I don't want to think that. So I assume that someone will follow up with this technology. But funding research is extremely expensive.
Sure. Oh, and I gotta say, my favorite prototype was the first prototype.
Yeah.
That's the one that caught my eye.
Well, it was demolished just the year I came here to King's State College, because it has been there for 8 years, and it was vandalized because it was working for 5 years. But I can't tell you, okay, come to Spain and I will take you to that prototype because it doesn't exist anymore. But it has been working for 5 years. Okay. But thank you for at least someone likes what I do.
Lito has a question. So Lito, if you want to unmute and go ahead and ask.
Yes, thank you, Lynn. Hi, Fernando. That was a fascinating presentation. And I think that the technology that you have been developing really is, it has a lot of potential, although it's still costly, as what you have emphasized. Now, my question is just out of curiosity. I suppose that the type of water that is being used in this technology is fresh water. However, hypothetically, for instance, the person would want to use this in a remote island wherein there is no ample amount of fresh water. How would salinity of the water affect the efficiency of the technology?
It's not fresh water. So
it's not, okay.
No, you can't take this water from the tap. It's like, imagine that in a car, we do have water. Well, we have a lot of fluids. Well, we do have water for the wipes, but it's a fluid. So we call it water because it's more appealing, but it's not water at all. So it's more alcohol than water. Okay. So you but the optical properties of water are affected by those additives. So you have to be very careful. It's like a formula. Okay. So there's a secret formula. I told you that there are patents, but yeah, so if you want to find out, I can tell you, okay? Because it doesn't have to be in a public speech.
All right, thank you.
Can I ask a question?
Sure.
Oh,
Yes.
This is Mehdi. Thank you very much, Fernando. It's a great presentation. I've learned a lot. I have a question about the glazing, water glazing. So if we have an argon between the two glazing, and we also have a water flow between the two glazing, so the argon will move. So this movement does increase the conductivity, so the U value will increase.
That's again a very good question. The movement of the water, I showed you a formula about how this U value can be dynamic. And of course, moving water or moving something, it affects the thermal transmittance of this panel. But at the same time, you have to take into account the absorption of the water, and you have to take into account the difference between the inlet and the outlet temperature. So it's too complicated. And to be honest, I am the architect here. So I know something about physics. I know about building physics, but I think you have to ask another members of my team about all these questions, because yes, it's very complicated, and came up with a formula that explains this. I have to study, okay? I can't answer this question just from the top of my head. I have to study, and then I could answer you this question. And you are right, moving things affect the thermal conductivity and the physics. It's very difficult. So that's why it's a success. The first prototype, we lost a lot of money. We didn't have the comfort in the middle of the desert, but at least we validated the thermal model, the mathematical model, which is very complicated.
Thank you, Fernando.
Thank you, Betty.
Okay. If there are no other questions, Fernando is still here. You can talk to him a little bit after.
Yes.
And until then, I say thanks very much, Fernando.